Okay, and I have a little activity for you here. So now we're going to talk about graphing quadratic functions of the form f of x equals ax squared. And I just realized something. Okay, so we're going to look at the graphs of these functions. F of x equals x squared, g of x equals 2x squared, h of x equals 1/3 x squared, and then p of x equals negative x squared. And what I just realized is that I did not set up a column for p of x. On the next slide I did. All right. So we'll just add one over here. I'm actually going to ask you to pause the video and try this. All right, just fill in the table and then draw the graphs. All right, and then when you're ready, come back and we will compare notes. Whoops. All right, here we go. So table is all filled in, and I used a certain website that I like to draw these graphs. So let me explain what you're looking at. The one in blue here that's sandwiched between these other two, that is your regular old f of x equals x squared, okay? The one above that is g of x. I wish I had an easy way to label these. They have this color key over here, but these, I don't know, these colors, at least to me, are kind of difficult to see. Okay, so maybe what I'll do, okay, this one here, I'm doing this with my mouse, so if it looks terrible, that's the reason why. This one here is g of x. This one here is f of x. Okay, the one below that, but still opening upwards, is h of x. And then the one down below that's opening downwards is p of x. Now you already actually know something about this. In chapter 8, we talked about reflections across the x-axis. So you should have already known that p of x, that the graph of p of x would be a reflection across the x-axis of the graph of f of x. And by the way, I'm shocked at how good these look. However, we never talked about what's called stretching and shrinking. I talk about that in pre-calculus. Notice that the graph of g of x, which is up here, looks like somebody took the graph of f of x and stretched it upwards, all right, made it skinnier, all right, but kept the vertex nailed down at 0, 0. And then h of x, which has the 1/3 in front, that's like somebody took f of x and squashed it down, all right, made the parabola open wider. All right, so now I'm ready to let you in on the secret behind how this works in general. All right, first of all, if a, all right, in f of x equals ax squared is positive, then the parabola opens up. If a is negative, the parabola opens down because that means a reflection has taken place. And there is a really cute way to remember this. All right. The smiling face with the little plus signs for eyes helps you remember that if a is positive, the parabola opens up. And the little closed eyes with the frowning face, the sad face, helps you remember that if a is less than 0, the parabola opens down. Okay. And then the other piece to this is that if the absolute value of a is greater than 1, which is another way of saying that the value of a is further from 0. It's a number like 2 or 3 or -4, all right? Bigger than 1 in either direction, all right? Without getting more technical than that. So if the number is further away from 0, it makes the parabola narrower. But if the value of a is closer to 1, which usually means a fraction, 1/2, 1/3, -1/4, then that makes the parabola wider. It means it's been squashed down. All right, so here are a couple of examples. Y = 5x squared is a very narrow parabola. Y = 0.2 x squared is a wider parabola. Regular old y = x squared would be right in the middle here somewhere. Okay, so graphing quadratic functions of the form f of x equals a times x minus h squared plus k. So what's happening here is that we start with our regular y = x squared, and then we shift the graph horizontally, we stretch it or shrink it, and then we shift it up or down. All right, so possibly all three of those things. The vertex of this function will be at the point hk, and you have to be careful with your signs. I'll talk about that when we do an example. Note whether the parabola opens up or down. That's just based on the value of a. And then I always recommend making a table of x values centered at the vertex. And again, you will be able to use your symmetry. All right, so let's look at these two examples in MyLab. All right, so the last two examples are going to be problems 8 and 9 from the homework, starting with number 8. Same directions as before, and this time the function is f of x equals -2 times x plus 4 squared plus 1. So let's talk first about the vertex. Remember that we're matching this up to the form a times x minus h squared plus k. The vertex is the point hk. All right. So I just realized I'm writing on my tablet and you can't see my tablet. Okay, but I don't think you missed too much. All right. All right, so there it is. A times x minus h squared plus k. The vertex is at hk. So the thing that you have to be careful about is the minus sign in front of that h. That minus sign is built in. So when you see something like an x plus 4, you really need to think of that as x minus -4. It means that h is -4. All right, but there's nothing tricky about k. K is going to be 1. Okay. All right, so now let me make my table. Again, we can take advantage of the symmetry, so I'm going to leave space here for 5 points. However, we really only need to calculate 2 points. We already know that the y value that corresponds with -4 is 1. So if I just pick two values that are greater than -4, like -3 and -2, then I can use the symmetry to fill in 2 other points. All right, so let's do this. We have -2 times blank plus 4 squared, add 1. All right, so if we put a -3 in there, -3 plus 4 is 1. 1 squared is 1. -2 times 1 is -2. -2 plus 1 is -1. All right. So the y value that goes with -3 is -1. And so if we mirror that across the vertex to -5, which is 1 unit to the left of the vertex, that's also going to be a -1. All right, and now doing the same thing with -2 for x. if I put my -2 here, -2 plus 4 is 2. 2 squared is 4. -2 times 4 is -8. -8 plus 1 is -7. All right, so that's for -2. If we mirror that across the vertex to -6, which is 2 units to the left of the vertex, that is also going to be a -7. All right, so let's look at what this is going to look like before we do it on the computer. Let's see, first of all, okay, this time my X scaling is okay. But you know what? I'm going to use the same scale for both X and Y. You don't necessarily always have to do that. But in this case, I think it would be a good idea. So once again, I'm going to make each one of these worth 2. And also on the Y. All right, my vertex was at the point -4, 1. And then I had a point at -3, -1, which is right about here. And I had a point at -2, -7, which is all the way down here. Okay, because of that -2 in front, that does 2 things. Because of the negative, it flips the graph upside down. And because of the 2, which is further away from 0, it makes the parabola skinnier. So this parabola is going to look something like this on the right side, and then mirror image on the left side. Get these other points in here. Okay, it's going to look a little something like that. All right, so now let's look at it on the computer. All right, so popping this out, picking my vertical parabola tool. First, it wants the vertex, which was -4, 1. And then it wants just one other point. I'll use -3, -1. And have you ever noticed up in that top right corner of the graphing area, you can see what point you're at? That's helpful. So that says -3, -1. Okay, so now the parabola is done. And I have to draw my axis of symmetry. So I click on the line tool. My first point will be the vertex, and my second point, I'll just do something like that. And then don't forget to make it a dashed line. All right, so now that should be all done. We will hit check answer. Woohoo! The vertex is -4, 1. And what's the equation of the axis of symmetry? It's x equals -4. All right. So now for our last example, let's look at f of x equals 1/4 x minus 2 squared minus 3. Switching over to the tablet. All right, here we go. So remember a x minus h squared plus k. All right, so this time I do get the minus with the h. All right, x minus 2 is x minus h. So that just means that h is 2. Everything else in there is the same. Okay, but now the sign in front of k is different. Plus k is equal to -3. So that means k is -3. So the vertex is 2, -3. This parabola will open up. I forgot to say that about the last example. I could tell by looking at that -2 in front that it was going to open down. This one is going to open up. And it's going to be a wide opening parabola because it's a 1/4, which is closer to 0. Okay. So now I'm going to make my table, and I'm going to do something a little different, a little sneaky. All right, still going to think about 5 points. And I'm still going to put my vertex right in the middle. However, this time I am not going to use 3 and 4 for my other values of x. I am going to use, believe it or not, I'm going to use 4 and 6. And the reason I'm using 4 and 6 is because I would really like that x minus 2 squared to be a multiple of 4, because it's going to get multiplied by 1/4. All right. So you'll see how that's going to work here in just a second. We already know that the y that goes with x equals 2 is -3. Oops. Okay, so now for x equals 4, let's put 1/4. I hope I have enough room to do this. Blank minus 2 squared minus 3. Filling in the blank with a 4. All right, here we go. 4 minus 2 squared is 2 squared. 2 squared is 4. I'm going to have to cheat a little bit here. And 1/4 times 4 is 1. That's the reason I used x equals 4 instead of x equals 3. Otherwise, it would have come out to a fraction. Okay, so the y value here is -2. So what would the mirror image of that point be? Let me make this a little bit clearer for you in case it didn't make complete sense before. The point where x equals 4 is 2 units to the right of the vertex. So now I'm ready to talk about the point that is 2 units to the left of the vertex, and that would be at x equals 0. So we know by symmetry that the y value that goes with that point is -2. All right, and then 6, x equals 6. This is really going to be tight. Let me put a line here so this doesn't all get mixed up. Okay, 6 minus 2 is 4. 4 squared is 16. And then 1/4 times 16 is 4, right? 4 minus 3 is 1. Okay, so we have the point 6, 1. This point is 4 units to the right of the vertex, so we also need the point that is 4 units to the left of the vertex, and that's going to be at x equals -2. The y value that goes with that point is 1. All right, so we have all these points. Oh my gosh, I think this time I can use a regular scale. I can just leave my graph exactly the way it is. Vertex is at 2, -3. And then we also have a point at 4, -2, and we have a point at 6, 1, right? Okay, so the right half of the parabola looks like this. This is our wide opening parabola. And because of the symmetry, I know that I also have this point and I have this point. All right, so now we'll go back to the computer. We'll put in that answer and we'll be done with this section. All right, here we go. Pop this out, hit the vertical parabola tool, plot the vertex, which is 2, -3. Click any other point on the parabola. I'll go with 4, -2. Okay, so that should be good. And then my axis of symmetry, click the line tool, first point, vertex, second point, anywhere above or below, and then don't forget to make it a dashed line. All right, so that should be good to go. Yahoo! All right, what is the vertex? The vertex is 2, -3. And the axis of symmetry is x equals 2, right? All right, and that's about all you're going to see in this section. Next section will be more graphing quadratic functions, but when the functions are in a different form. All right, so we'll see you next time to talk about that.